Hello friends, so today we are going to solve questions from modern physics. And these questions are from the year 2015, and from 2015 there are total 7 questions. One question is from the mains, and six questions are from advance. And for 2016 we are having 2 questions from the mains and 6 questions from advance. So in total we are going to solve 15 questions. First question, it was asked in the 2015 mains, and it states that as the electron makes a transition from an excited state to the ground state of an hydrogen-like atom or ion, then we have to check the 4 options which are related with increase and decrease of the potential energy as well as total energy, or remain same. Okay. So it is said that we are having a hydrogen-like atom or ion, therefore we can write the equation that total energy E, that is given as minus, rather E of n 13.6 z square upon n square, and it is given in terms of our electron volt. And if you see this equation, in this equation our energy is represented by a negative sign, okay, and it increases in magnitude as n decreases. As n decreases, and our kinetic energy it is suppose given as k, and that will equal to our minus of E. So obviously this will be positive, and potential energy is suppose given as U, and that will be equal to our twice of E, or we can also write it in the formation of our kinetic energy, or we can say that will be equal to minus 2 times K, and that is negative. So therefore, as electron jumps from excited state to the ground state, or we can say from the higher one to the lower one, has electron transitions from excited to a lower to a ground state is asked here. Let's write ground state. Ground state. Then first of all it is asked for the total energy. So you can say our total energy becomes more negative or decreases. More negative, or we can say decreases. Next, now we ask for the potential energy. So potential energy becomes more negative because potential energy is also dependent upon total energy. So potential energy becomes more negative, that is decreases. And finally we are left with our kinetic energy. Kinetic energy increases because our total energy E becomes more negative. So we have a increase in the kinetic energy, and we have decrease in potential energy as well as decrease in total energy. So we can say that we are having kinetic energy increases, potential energy and total energy decreases. So option D is correct. Next question. It was asked in the 2015 advance and states that for photoelectric effect with the incident photon wavelength lambda, the stopping potential is V0. Identify the correct variations of V0 with lambda and 1 upon lambda. Okay. So in this case, we have to find a relationship between our V0, that is lambda, as well as 1 upon lambda. So we can start with our photoelectric equation. So photoelectric equation, and it gives us E times V0 is equal to H C upon lambda minus of phi. And in this case, we can write that our V0 will be equal to Hc upon E 1 upon lambda minus phi upon E. So first of all, let us see how V0 versus lambda. So in this case, you can see that there is, we can say, hyperbolic or inverse relationship between the two. So we can write this is hyperbolic or inverse relationship. Secondly, we can understand that as lambda is going to increase, this V naught is going to decrease. You can say lambda increases, V naught decreases. Thus, we can write that V naught versus lambda, the graph will be our non-linear and decreasing. So non-linear and decreasing. So non-linear are only options available to us are option number A as well as option number D. So it is decreasing, so you can say option A is correct. A is correct. And next is our V naught versus 1 upon lambda. So we are going to use same equation but in a different way. That is our V naught is equal to Hc upon E 1 upon lambda minus phi upon E. And because here the variation is with respect to 1 upon lambda, so we can say from here that there is a linear relationship between V naught and 1 upon lambda. Linear relation between V naught and 1 upon lambda. And in the intercept form, we can say the slope is given as Hc upon E. Slope will be our Hc upon E, and its y-intercept it will be given as minus phi upon E. So therefore, there is a linear relationship V naught upon 1 lambda. This gives us that there is a linear increase so there are only two graphs which are representing the linear relationship B and C, and with respect to linear increase, option number C is correct. Next question. It It was asked also in the 2015 advance, and it states that for a radioactive material, its activity A and rate of change of its activity R are defined as A is equal to minus dN upon dt and R is equal to minus dA upon dt, where Nt is the number of nuclei at time t. Two radioactive sources P mean life tau and Q mean life 2 tau have the same activity at t is equal to 0. The rate of change of activity at t is equal to 2 tau are Rp and Rq respectively. If Rp and Rq ratio is equal to N upon E, then the value of N is. So we are given two sources with the different mean life, but initially they are having the same activity. So one source is our P. We have a source P and its mean life is given as tau. We have source Q and its mean life, it is given as 2 tau, and it said that at t is equal to 0 they are having same activity. At t is equal to 0, the activity of P is equal to activity of Q, and we are also given that activity of both at any time t, that is our A of t, is given as minus dN upon dt, which can be also written as lambda n times n of t, and the rate, that is R of t, is given as minus dA upon dt. And here we are going to use decay law and activity. So we can say that decay law and activity and let me write it here. For source P the mean life is tau, therefore from here we can say that is a decay constant. Let us suppose that lambda P will be equal to 1 upon tau, and for source Q, let us suppose that lambda of Q is equal to 1 upon 2 tau, and therefore we can say that N of P at a time t will be equal to initial activity, that is our 0 e raised to the power minus t upon tau, and we can write this as our activity with respect to AP, that is our derivative of this. So we derivate it, we get this as 1 upon tau np0 e raised to the power minus t upon tau, and similarly for our source Q we can write this as nqt is equal to nq initial e raised to the power minus t upon 2 tau. Therefore we get aq of t is equal to 1 upon 2 tau nq0 e raised to the power minus t upon 2 tau, and we can find out the activity at t is equal to 0, which is given to be same. So we can say at t is equal to 0 we get our AP0 will be equal to, substituting in this equation, we have 1 upon tau, and this is our 1 np0, and we get our A of q, similarly 1 upon 2 tau, and this have nq0, and both are given equal. Therefore we can write that 1 upon tau np0 is equal to 1 upon 2 tau nq0, and here tau goes with tau, so we get the relationship between initial activity nq0 is equal to twice of np0. Sorry, not the relationship with activity, but at any time t. Okay. No, initial sample at 0. Sorry, activity was given as same, but we found out that initial sample at 0 for both the cases, we get the relationship. Now we can use rate of change of activity. Rate of change of activity, which is given to us as R is equal to minus dA upon dt, and which can be written as minus T of dt lambda times n, and which can be further written as R is equal to lambda, we can take as common, so this becomes as, no sorry, outside, and this becomes our dn upon dt, and this gives us lambda square times n. So once again, with respect to two samples, we can write that our of p sample R of p will be equal to lambda p square, and this we have n of pt we get from here in terms of tau whole square, and we have this as n of p0 e raised to power minus t upon tau. Similarly, we can write for our q, we had R of q is equal to lambda q square, and qt is equal to 1 upon 2 tau whole square, and we already know that relationship between our np0 and npq0, so we can just write in terms of twice np 0 e raised to power minus t upon 2 tau, and we are supposed to find out at t is equal to 2 tau. So if we take the ratio and substitute t is equal to 2 tau, so we can say ratio rp upon rq at t is equal to 2 tau, and this can be written as rp is our 1 upon tau square np0 e raised to power minus 2 tau upon tau, and our rq is our 1 upon 4 tau square 2 times np0 e raised to power minus 2 tau upon 2 tau. So we tau square, np naught, 2 tau and tau cancels out. So we are left with this will be our one upon 4, and okay, this also we can cancel out. This becomes as 2. So this comes as 2 is equal to e raised power minus 2 and e raised power minus 1. And now it is quite easy. So this becomes as 2 e raised power minus 1, on which can be written as 2 upon e. And it was given as n upon e. N upon e. So from here we can say that value of n is equal to 2. So value of n is 2. Next question. It was also asked in the year 2015 advance, and it states that a nuclear power plant supplying electrical power to a village uses a radioactive material of half-life T years as a fuel. The amount of fuel at the beginning is such that total power requirement of the village is 12.5% of the electric power available from the plant at that time. If the plant is able to meet the total power needs of the village for a maximum period of n t years, then the value of n is. And the important part is that the village requirement is 12.5% of the electrical power available at that particular time. Okay. So if you assume that initial power requirement at t is equal to 0, let us suppose is a P naught. Therefore, village requirement at same time will be equal to 12.5% of P naught, or we can write this as 1.8 of P naught. And we can solve this, you can say, question using two approaches. So let me solve this in the first way, and then we can use the second part also. And please remember that it mentioned that the amount of fuel at the beginning is such that total power requirement of the village is 12.5% of the at that time. So we have to keep this relationship in mind. So after time t, or we can say at time t, the power available because we are given this is a basically radioactive material, so we can reformulate the radioactivity equation as P of t will be equal to our initial, and we have this as 2 raised to power minus t upon tau. And we have to find out that at t is equal to nt, this relationship that P of t is equal to 1 upon 8 P naught should be satisfied. So we use this condition and we can write that our P naught e raised to power, sorry, not e, 2 raised to power t is given to us as nt upon tau is equal to 1 upon 8 times P naught. And one second, yes, this is capital T, my mistake. And this goes away, P naught goes away, so we are left with only 2 raised to power minus n is equal to, and 1 upon 8 can be written as 2 raised to power minus 3. This gives us value of n is equal to 3. Okay, answer will be coming same in both cases. Value of n is equal to 3, and we can use also the traditional relationship which gives us the let me do it the second way. And we have said that at n is equal to t upon th, we can write that our radioactivity n will be equal to n naught raised 2 raised to power n. And our requirement, it is given in the question that requirement is requirement of total power, requirement of power is 12.5% of total power. So it means we can say that our value of n will be equal to 12.5, and from here we can write that our n is equal to 12.5 upon 100 times n naught. And we already know relationship between n and n naught, we equate them. So we get from here as n naught upon 2 raised to power n is equal to n naught upon 8, and this gives us same, that is value of n is equal to 3. Okay, there is not much of the difference between the two. And next question. It was also asked in the year 2015 advance, and it states that a fission reaction is given by U is equal to two products X and Y. X and SR are the main products, and X plus Y, where this X and Y are two particles. Considering uranium to be at rest, the kinetic energy of the products are denoted by Kxe, Ksr, Kx, and Ky. The kinetic energy of Kx and Ky are given to us respectively. Let the binding energy per nucleon of uranium X and Sr be 7.5, 8.5, and 8.5 respectively. Considering different conservation of law, the correct option is or are. Here I'm sorry, I just forgot to put the options, but anyways we can get the results directly. And first of all, let's write the given equation. We are given that our uranium is going to give us X plus Sr plus X and Y. And uranium, then we have our X is our xenon, Sr is our strontium, and X and Y are the particles. Okay. So first of all, we are going to use the nucleon conservation. So you can say that nucleon conservation and on the left side we are having only uranium. So on the left hand side we have our uranium, which gives us 236 nucleons, and on the right hand side we have our X. I think it should be, it should be Xe or X, I'm not sure about it. Okay, but let's put it Xe, otherwise yeah, I think it should be Xe, xenon. Yeah, it's Xe, here it is written. So then we have our xenon, and this gives us 140 nucleons, and the other term which is on right hand side is our strontium, and this gives us 94 nucleons, and the total of these two is coming as 234 nucleons. So the difference between the left side and the right side is 2. So we can say that our 2 nucleons are missing. So from here we can say that our X will be equal to N and Y will be equal to N. Okay, that is about 2 neutrons. Okay. And next is our related with energy. So we can say energy released and total binding energy of our is uranium is given as 7.5. So we can say, and it is given as per nucleon. Therefore we can write that total binding energy for uranium is equal to 236 multiplied by 7.5. This will be coming as 1770 mega electron volt. And for our right hand side, we can write that our binding energy for xenon will be equal to 140 multiplied by 8.5. This will be giving us 1190 mega electron volt. And binding energy for our strontium will be equal to 94 into 8.5. This gives us 799 mega electron volt. So total this comes as 1989 mega electron volt. So therefore we can find out the difference between the two, which will be giving us the amount of energy released. So we can say energy released, which is our Q value. This will be giving us 1989 minus 1770, giving us 219 mega electron volt. And next we are going to find out with respect to kinetic energy, because we are given that the kinetic energy for our X and Y are given to us. So we can say that kinetic energy consideration and we are given that K of X plus K of Y, it can be written as K of N plus K of N is equal to 2 plus 2, which is given as 4 mega electron volt. Therefore the energy, remaining energy, will be associated with our strontium and xenon. So we can write that total remaining energy for Xe and Sr, and we can write the same equation, K Xe plus K Sr, total energy Q released is our 219 minus 4, giving us 215 mega electron volt. Now we can use our conservation of energy, momentum conservation. Momentum conservation, and here we are having two particles, because our X and Y are of same, then we are only left with our xenon and strontium. So with respect to momentum, we can say the heavier particle is going to have, or we can say heavier fragment is going to have less kinetic energy as compared to the lighter one. You can say heavier fragment which is our xenon should have less kinetic energy than lighter one, which is our strontium in this case. Okay. And this particular part we are going to value, because if I remember correctly, the options were given such that for xenon, kinetic energy for xenon rather, kinetic energy of xenon were having a 86.86 mega electron volt, and kinetic energy for strontium was having 129 mega electron volt. Okay. So these particular values we chose from the options that were given to us. Okay. And this combination is given in the option. And if we add these two, obviously the total has to become 215. Okay, because we know that the combination should be 215. So we have to keep in this mind. So the options that should be selected is our x should be equal to n, y should be equal to n, and our kinetic energy of our strontium will be equal to 129 mega electron volt, and kinetic energy for xenon should be equal to 86 mega electron volt. Okay, so this option will be the correct one. Next question. It was also asked in the 2015 advance, and it states that an electron in an excited state of lithium 2 positive ion has an angular momentum of 3h upon 2 pi. The de-Broglie wavelength of the electron in this state is p pi a naught, where a naught is a Bohr radius. The value of p is. So we are given that angular momentum. So we can use the standard equation for angular momentum and find out value of n. Angular momentum, that is our L, it is given as nh upon 2 pi. So for this particular question it is given as 3h upon 2 pi. This gives us that value of n is equal to 3. And now we can find out, or we can say radius for the orbit. Standard formula is our for r of n, which we can substitute value of n is equal to 3. So we can say radius of orbit, that is our r of n, is equal to, we have our a naught and z square upon n, and we know the value of n, and z also we know. Z is our 3 for lithium 2 positive ion. So therefore we get our r of 3 is equal to, this comes as 9 upon 3 times a naught, which gives us that R of 3 is equal to 3 times A naught. Next is we have to find out de-Broglie wavelength, and for that you can say that for stable orbits we should be satisfying the condition that 2 pi times R of n is equal to n times lambda. So we are required for our lambda, so lambda will be equal to 2 pi R of n divided by n. We already know our n is 3, so this will be equal to about 2 pi R of 3 divided by 3. R of 3 we already know is about 2 pi 3 times A naught and divided by 3. Here 3 and 3 cancel out, so we get that our lambda will be equal to 2 pi A naught. But given value of wavelength is pi p A naught. Okay, so we are given, we found out lambda is equal to 2 pi A naught, but it is given as p pi A naught. So from here the value of p is equal to 2. So value of p is 2. Next question. It was also asked in the 2015 advance, and it states that calculate a hydrogen atom with its electron in the nth orbit and electromagnetic radiation of wavelength 90 nanometer is used to ionize the atom. If the kinetic energy of the ejected electron is 10.4 electron volt, then the value of n is, we are given Hc is equal to 1242. And we have to find out value of n, and for that we are going to start with finding out the energy of the photon. So we can say energy of the photon E photon is equal to Hc upon lambda, and we substitute the values. So we get energy of photon is equal to Hc is given as 1242, lambda is 90, and this gives us approximately as 13.8 electron volt. Now we can use energy conservation and find out the binding energy for the orbit. And we can say energy conservation which gives us that energy of photon will be equal to energy for the binding plus kinetic energy. Kinetic energy is given to us as 10.4, therefore we can write that energy for our binding energy of photon is our 13.8 minus 10.4. This gives us that our binding will be equal to 3.4 electron volt. Or in simpler terms, we can say that the binding energy for electron in the nth orbit is 3.4. We can say binding energy of electron in nth level is 3.4 electron volt. Now we can use easily our Bohr energy formula. Which is nothing but our E of n is equal to minus 13.6 upon n square electron volt. And for nth, in terms of magnitude, we are given as 3.4. So we can say that our E of n in terms of magnitude will be equal to 3.4, and which in term will be equal to 13.6 upon n square. So this gives us that our n square will be equal to 13.6 divided by 3.4, which is our 4, giving us value of n is equal to 2. I think this was value of n is our 2. Next question. It was asked in the 2016 mains, and it states that the radiation of the wavelength lambda is incident on a photocell. The fastest emitted electron has the speed v. If the wavelength is changed to 3 lambda upon 4, the speed of the fastest electron will be. So here we are having a photocell which will be same. First we are projecting a wavelength of lambda, and then it is being projected by the wavelength of lambda by 3 lambda by 4. For lambda, the velocity of fastest emitted is given as v, and for this we are supposed to find out. This is the basic premise of the question. And so we are given that radiation of wavelength is our lambda, and in this condition the electron velocity is given as v, and now the wavelength is changed, so you can say change wavelength. Let us suppose that is our lambda prime, which is given as 3/4 by lambda, and in this case we assume that the electron is having a velocity of v prime. So we have to find out relationship basically between v and v prime. That's what's required. So we can just use our start for the photoelectric equation, or we can say Einstein's photoelectric equation and this gives us the kinetic energy is equal to, which is a representation of half mv square, will be equal to hc upon lambda minus phi. And we are interested in our velocity only, so we can just ignore this particular part and we can write this equation in terms of proportionality, that V square is proportional to hc upon lambda minus phi. And now this was our, when the wavelength was our lambda, and now in this case, second case, we can say wavelength is of lambda prime. We can say for second case, velocity is our v prime, and this comes as hc upon lambda prime minus phi. We substitute value of lambda prime in terms of lambda, so we get our v prime square is hc upon 3 lambda by 4 minus work function. Let's find out the ratio. So we get from v prime square upon v is equal to hc upon, this can be written as 4 by 3 upon lambda minus phi, and in the denominator this is a square hc upon lambda minus phi. And if we make a comparison with respect to the ratio, so from the right side we can clearly see that our 4 by 3 hc upon lambda minus phi will be greater than hc upon lambda minus phi. Okay, this is quite obvious. Therefore, okay, therefore at least we can write that this particular expression will be greater than 1. Okay. And based on the options that are given to us, only option that is the correct option greater than 1 is option number A. Okay, because it cannot be equal, or obviously it cannot be less than. Therefore, we can write that our v prime upon v is greater than square root of 4 by 3, or we can say v prime is greater than v 4 by 3 and 1 by 2. So option A is correct. Next question. It was asked in the 2016 advance, and it states that in a historical experiment to determine Planck's constant, a metal surface was irradiated with the light of different wavelengths. The emitted photoelectron energy were measured by applying a stopping potential. The relevant data of the wavelength of incident light and the corresponding stopping potential V0 is given below. The Planck's constant is, so basic table is given to us, that how our lambda and V0 are related with each other. Okay. And we start with our basic equation, then we are going to use the data that is given to us. So you can say that our photoelectric equation which gives us E times V naught is equal to hc upon lambda minus phi. So we get V naught is equal to hc upon E 1 upon lambda minus phi and phi upon E. So this can be written and in the format we are having a V naught is equal to hc upon E 1 upon lambda, and we can write this as plus some form of a constant. Therefore, if we plot between V naught and 1 upon lambda, this is a linear relationship. Okay, because almost same type question was asked in the 2015 also in terms of the plotting of the between V naught and 1 upon lambda. Okay. So therefore we can say that plotting V naught versus 1 upon lambda, which is our giving us a slope, will be equal to hc upon E, or we can, based on the given values, we can write that lambda is given to us and V naught is given. So we have lambda and V naught, but we are plotting with respect to 1 upon lambda, so we are going to find out 1 upon lambda. So lambda is our 0.3, stopping potential is 2, sorry, it is 0.3. One upon lambda gives us 3.33. Then we are having 0.4, 1, and 1 upon lambda will be equal to 2.5. And finally we are having 0.5 and 0.4. This gives us 2. So because the relationship between, or we can say that this particular equation is going to give us a graph which will be linear, because we are plotting between 1 upon V naught is equal to versus 1 upon lambda, not only lambda. If it's lambda, then it is inverse relationship, so obviously graph will not be linear. Okay. So in this case we are going to take 2 points. So we can say choose 2 points. Let us suppose first point we have taken as x1, which is our 2, and v1, that is our 0.4. Okay, so this is our first point we have taken, and second point is our x2 is equal to 3.33 and v2 is equal to our 2. So this is our second point. So based on this we can easily find out our slope. So we can say that our slope will be equal to delta V naught and delta of 1 upon lambda. So we have this as 2 minus 0.4 and we have 3.33 minus 2. So this gives us 1.2, and Therefore, in the general equation, the slope is given as hc upon E, and the actual slope which we found out is 1.203. So we can just equate them. So we can say, therefore we can say our hc upon E is equal to 1.2, not 0, 0.03, and we already know all the values, so here we can just substitute them. We get hc is equal to, we have this as 1.203 multiplied by our charge, that is our 1.6 into 10 to the power minus 19, and one second, 1 point, okay, first of all we have to convert into SI units, otherwise this won't work. We can say, converting to SI units, SI units. So we get that we need value of Planck's constant here. So we can write that our H upon E will be equal to 12.023 electron volt and per micrometer, not per but micrometer. Then we can just substitute the values. We get this will be equal to 12.03 into 1.6 into 10 to the power minus 19 into 10 to the power minus 6 because of the micrometer, and this comes as 1.9248 into 10 to the power minus 25, and therefore now we can easily find out value of Z H. Therefore we can say H will be equal to Hc upon E and multiply by E and divide by C. So this will be equal to 1.9248 into 10 to the power minus 25, and this comes as 3 into 10 to the power 8. This gives us approximately equal to 6.6 into 10 to the power minus 34. Next question. It was asked in the 2016 mains and states that half-lives of two radioactive elements A and B are 20 minutes and 40 minutes respectively. Initially, samples have equal number of nuclei. After 80 minutes, the ratio of decayed number of A and B nuclei. So we are given two elements and their respective half-lives, and initial they are having same nuclei, number of nuclei. So you can say for element A, T half is given to us. So you can say this as T half for element A will is equal to 20 minutes, and we can say for B, T half for B is our 40 minutes. And initially they are both having same number of nuclei. So we are given that initial number of nuclei for A and B are same. So we can write that our N naught for A will be equal to N naught for B, and we have to find out that after time T is equal to 80 minutes. You have to keep this in mind. So we can use the decay formula. And which gives us N is equal to N naught 1 by 2, and this is T divided by T half. So we have two elements A and B, therefore we can write for A, we have N of A is equal to N naught A multiplied by 1 by 2, this is 80 and divided by 40, 20. This gives us our N naught A and divided by 16. Similarly, we can say for B, we have this is NB, N naught B is equal to 1/2, this is 80 divided by 40, this comes as our N naught B divided by 4. So we have to find out the ratio of decayed number. So we can write that decayed nuclei will be equal to initial nuclei minus remaining nuclei. Initial minus remaining. Initial was our N naught, and it is given that they were same. Okay, so initial were same, so we can just write this will be equal to our N naught. So we can say that for A, decayed is our D of A is equal to N naught minus N of A, and this can be written as N naught upon 16 and this not N naught upon 4 because they are same. Therefore we get N naught minus N naught upon 16. This gives us 15 upon 16 times N naught. Similarly for B, we are having N naught minus NB, giving us N naught minus N naught upon 4, which will be giving us 3 by 4 times N naught, and we are going to find out the ratio. So we can say that their ratio will be equal to 50 upon 16 times N naught, and we have 3 upon 4 times n naught. This gives us 5 upon 4. Option D is correct. Next question. It was asked in the 2016 advance, and it states that an accident in a nuclear laboratory results in the deposition of a certain amount of radioactive material of half-life 18 days inside the laboratory. Tests revealed that radiation was 64 times more than the permissible level required for safe operation of the laboratory. What is the minimum number of days after which the laboratory can be considered safe for use? So we want that the radiation should be to the permissible level, but initially it is given as 64 times the permissible level. So we are given that initial radiation level is equal to 64 times permissible level, and half-life is given as 18. So we can use the decay formula. Radioactive decay formula, and we know that the radio intensity decreases by a factor of 2 for every half-life. So we can say that radioactive intensity decreases by a factor of 2 every half-life. Therefore, we can say that 1 by 2 raised to power n is equal to 1 upon 64. So therefore, from here we can find out the value of n. So we get value of n is equal to 6. Thus, we can say that the 6 half-lives are required. 6 half-lives are required. Now we can just find out the time, because for one half-life it is 18 days. So you can say that time required is equal to 6 times 18, which gives us 102 days. So option number C is correct. Next question. It was asked in the 2016 advance, and it states that a hydrogen atom is in its ground state is irradiated by a light of wavelength 970 angstrom, taking Hc upon E as 1.237 into 10 to the power minus 6 EVM, and the ground state energy of hydrogen atom as minus 13.6 electron volt. The number of lines present in the emission spectrum is. So first of all, based on the wavelength, we are going to find out the energy of the photon. So energy of photon, E is equal to Hc upon lambda, and we get this as 1.237 into 10 to the power minus 6, 970 into 10 to the power minus 8. This comes approximately as 12.75 electron volt. And let's find out because the hydrogen atom is in its ground state, and let us suppose it moves to the higher state n. Okay, so let's find out the energy associated with this nth level. So we can say final energy n. Final energy at level n. For ground state we are given ground state value of n is equal to 1. So we can say our E of 1 is equal to minus 13.6 electron volt. And for nth level, the general formula we already know. You can say for nth level, we can write that E of n is equal to minus 13.6 upon n square. Therefore, the energy absorbed total energy absorbed, let us suppose that is our delta E, will be equal to E of n minus E of 1. We substitute their respective values or equations, and we get this as, because delta of E, let me call this as delta of E, is our 12.75. So we substitute it, we get 12.75. For nth is our minus 13.6 n square. For the first it is minus of minus 13.6. So we can take 13.6 as common, or minus 13.6, and we are left with 1 upon n square minus 1. Now it is only simple calculations, so we can write this as 1 upon n square is equal to this will be 1 minus 12.75 upon 13.6, approximately 1 minus 0.0625. So we can say that our n square, Is my mistake. This is 1 minus 0.9375. This will be equal to 0.02, which gives us that value of n square is equal to 16, giving us value of n is equal to 4. So we found out that it moves from first level to the fourth level. Okay, we have to find out the spectral lines. So you can see number of lines is equal to n into n minus 1 divided by 2, which comes as 4 minus 1 divided by 2, giving us 6. Spectrum is 6. Next question. It was also asked in the 2016 advance, and it states that light of wavelength lambda ph falls on a cathode plate inside vacuum as shown in the figure. The work function of the cathode surface is phi, and the anode are a wire mesh of conducting material kept at a distance d from the cathode. A potential V is maintained between the electrodes. If the minimum de-Broglie wavelength of the electrons passing through the anode is lambda e, which of the following statements is or are correct? So basically we have to find out what is basically our lambda e, how does it behave, and how the potential difference is going to change for the certain condition. So we are going to start with our kinetic energy of photoelectrons. You can see that kinetic energy of photoelectrons which is governed by photoelectric equation. So that is our kinetic energy is equal to Hc upon lambda. Here lambda is our represented lambda ph minus our phi, that is work function. Now if we say that, or in the question it is mentioned that we have applied a potential of V, so obviously this V is going to further provide energy to the electrons or acceleration to the electrons. So we can say that the emitted electrons are accelerated by potential V. Therefore, total kinetic energy of electrons will be equal to, let us suppose we represent this as K is equal to Hc upon lambda ph minus phi plus the energy provided by the potential, that is V. And we already know the relationship of the de-Broglie wavelength in terms of energy. Therefore we can say de-Broglie wavelength lambda E is equal to h upon 2m upon k. So we substitute value of k, we get our lambda E is equal to h upon, this comes as 2m, and K is our Hc upon lambda pH minus 5 plus EV, and its square root. So one by one we are going to check these options, which states that if lambda pH is less than our Hc upon 5, and this calculation will be all based on this particular equation. So you can say option A, and it states that lambda at pH is less than our Hc upon 5. So under this condition, if lambda pH is less than Hc upon 5, you can say that photon energy is higher than the work function, higher than work function. And increasing pH, because in option A it says that lambda E increases at the same rate of lambda pH. It means we are increasing lambda pH, and then we are going to find out the effect of that on our lambda E. So you can see increasing pH, lambda pH rather, reduces photon energy. Which basically means that there will be less kinetic energy, or we can also say larger lambda E. And so obviously lambda E is going to increase, okay, because as we are increasing our lambda pH, lambda E is also increasing, but there is the relationship between the two is with respect to square root is also present. Okay. So we can say that lambda E increases, but not linearly. With lambda pH, okay, because due to square root dependence, due to square root dependence. So therefore option A is partially correct, but only problem is with the same rate. Okay, so this is incorrect. It is going to increase, but not at the same rate. So option A is incorrect. Incorrect. Now we come to the option B. It says that lambda is approximately halved when D is doubled. Okay. And from the relationship, you can see there is no mention of D in this particular equation. Okay. There is only, so it means that our de-Broglie wavelength is only dependent upon the kinetic energy, which depends upon voltage V, not on distance d. So d directly doesn't affect lambda E. Okay, in the simplest term we can say that our option B we can say d does not directly affect lambda E unless the field strength which is our V upon D is considered. But in this particular case our V is fixed, but here V, that is applied voltage, is fixed. Therefore option B is incorrect. Now we have our option C. Lambda E decreases with the increase in phi and lambda pH, which we have more or less discussed in option A also. So we have our option C. Option C, if we increase phi, that is a work function, increasing phi, this reduces the kinetic energy. Reduces kinetic energy, and which basically means that lambda E increases, and increasing pH, lambda pH, this reduces photon energy, or we can say less kinetic energy, so our lambda E increases. Therefore option C, it states that lambda E decreases with increase in phi as a lambda. So option C is incorrect. And we are left with option D, which would be correct ideally. For large potential difference, V is very much larger than phi upon E, lambda E is approximately halved if V is made 4 times. We can just prove it mathematically also. So option D, it states that the V is very much larger than our phi upon E, and therefore we can say our kinetic energy will be approximately equal to E times V. Therefore we can write our lambda E in terms of proportionality will be 1 upon V, and new wavelength, when the potential is being increased by 4 times, let us suppose that is our lambda E prime will be equal to 1 upon 4 times V and its square root, and this can be written as 1 upon 2 square root of V. This gives us lambda E upon 2. So it means under this condition the new wavelength is half of the original wavelength, which is basically asked here, is approximately halved. V is made 4 times. Okay. So lambda E is our half of the this. So option D is correct. Next question. It was asked in the 2016 advance, and it states that the electrostatic energy of Z protons uniformly distributed throughout a spherical nucleus of radius r is given by E is equal to 3Z multiplied by Z minus 1 E square divided by 4R 5R 4 pi epsilon naught. The measured masses of the particles neutron H1 HNO hydrogen nitrogen oxygen are 1 point this, 1 point this, and 1 point this, and 15 point this respectively. Given that the radii of both nitrogen and oxygen nuclei is same, that is 9 point is same, and one AMU is 9.315 sorry 931.5 mega electron per c square. C is the speed of light, and E square upon 4 pi epsilon naught is given as 1.44 mega electron volt. Assuming that the difference between the binding energy of nitrogen and oxygen is purely due to electrostatic energy, the radius of either of the nuclei is. So we have to find out the, because they are given, they are having same nuclei, same radius. It is, they are having the same radius. So we have to find out their respective radius, and the main equation is given to us. So it is also mentioned that the binding energy is only because of the electrostatic energy that is going to exist between nitrogen and oxygen. So let's find out what will be the binding energy. Okay. So let's start with our nitrogen. Binding energy of nitrogen, and Z is our 7, and value of N will be equal to over 8, that is 15 minus 7 giving us 8. Therefore we can write that our binding energy of nitrogen will be equal to 7 times Mp plus 8 times M of N and minus M of N and whole term multiplied by C square. So we are given the masses of particles of the neutron is given to us, so we substitute it, and this will be coming as 7 times 1.007825 plus 8 times 1.008665 minus 15.000109 times 931.5. So we can just write their final result because it is mathematically quite simple to solve. So we get for nitrogen it will be coming as 115.49 mega electron volt. Similarly, we are going to find for our oxygen. Binding energy for oxygen will be equal to 8 times, sorry, it has to be small, MP plus 7 times our Mn minus Mo and C square. Okay, and in this case Z was our 8 and our N was our 7. So we simply substitute their values. We get this as 8 times MP was our 1.007825 plus 7 times Mn was our 1.008665 and Mo was given to us as 15.00 3065 multiplied by 931.5. So we get that our binding energy for oxygen will be equal to 111.96 mega electron volt. Now we can find out the difference in their binding energy. Difference in binding energy delta Be is equal to binding energy for nitrogen minus binding energy for oxygen. Values are known to us. So binding energy for nitrogen is 5.49 minus 111.96, and this gives us 3.53 mega electron volt. And it states that between our nitrogen and oxygen there is only electrostatic binding energy, the difference in this. So we are going to find out the difference in electrostatic energies for our nitrogen as well as oxygen. So you can say difference in electrostatic energies, difference in electrostatic energies for our nitrogen. We can write this will be equal to our formula is given to us. That formula is our, let me write it here, that formula is our 3z z minus 1 and 5 pi 3z minus 1 e square upon 5r 4 pi epsilon naught. So we are going to use this formula to calculate their electrostatic energies. So E of n, we have 3 times z, so we get this as 3 times 7 minus 1, and we have this as 5r and we are left with our E square upon 4 pi epsilon naught, and this value of E square upon 4 pi epsilon naught is given to us. So we can write this will be equal to our 3 into 7 into 6, that is our 126 upon 5r, and E square upon 4 pi epsilon naught is given as 1.4 mega electron volt Fm. This comes as multiply by 1.44. Okay, the unit will be common for all, there is no, later on we can just sort it out. And next is our for oxygen, E of O will be equal to, this comes as 3 into 8, 8 minus 1 divided by 5r E square upon 4 pi epsilon naught, and this comes as 168 divided by 5r into 1.44. Now we can find out the difference in energy. So we get this as delta E will be equal to E naught minus En, and we have this as 168 upon 5r minus 128 upon 5r multiplied by 144. This gives us 42 upon 5r multiplied by 1.44, and equating binding energy by this difference in electrostatic energy. So we get delta BE is equal to delta E, and delta BE is our 3.53 mega electron volt is equal to 42 upon 5r into 1.44 into, and this is our mega electron volt Fm. Now we can just easily solve for our R, because mega electron volt cancel out both sides, only unit left will be our Fm. So we can say that value of R will be equal to 42.1.44 and divided by 3.53 Fm. This gives a value of R is approximately equal to 3.47. Value of R is approximately equal to 3.427 Fm. .47. So option number C is correct. Next question. It was asked in the year 2016 advance and states that highly excited states for hydrogen-like atoms, also called Rydberg states, with nuclear charge Z multiplied by E, are defined by their principal quantum number n, where n is very much larger than 1. Which of the following statements is or are correct? So we have to find out basically the change in their radii and the change in their energy along with the change in the angular relative. Okay. So we have to find out the relative changes in the radii, energy as well as their angular momentum. So let us start with our radius. So we know radius of the orbit R of n is equal to our n square a naught upon z, and it states that for two consecutive orbitals, so in every case it is two consecutive orbitals, so we can write that for two consecutive orbitals, and we have to find the relative change. Okay, so we can say for two consecutive orbitals, the relative change will be equal to r n plus 1 minus r of n divided by r of n, because we have asked for consecutive, so one is our n, another one will be our n plus 1. Okay, and we can write this will be equal to our, because a naught and z will be common for both, so we can directly write this as our n square n plus 1 whole square minus n square. This gives us 2n plus 1 divided by n square, and we are given that value of n is very much larger than 1, so this is approximately equal to 2 upon n. Therefore, the relative 2 is our nothing but constant, so we can say in terms of proportionality 1 upon n, and this relative is varies as 1 upon n, and so it is independent of z and varies as 1 upon n. So it means option A and B are true. So you can say option A and B are correct. Because there is no mention of z in this equation, and with respect to n it comes as 1 upon n. Now we come to the energy. Energy of the orbit, general formula we already know, that is our E of n is equal to n square minus z square r of h. Once again we are going to find out the relative, so we can just use the formula. So a relative, we can write this as our E of n plus 1 E of n divided by E of n, and this will be giving us and r of h okay, so this will be coming as our minus z square upon n square r of h, and here will be our minus z square r of h n plus 1 whole square this is minus minus plus z square r of h upon n square, and we are left with z square r of h cancels out, so we get this as 1 upon n square minus 1 upon n plus 1 whole square multiplied by n square. So we can take LCM, or we can multiply it by n square. So this comes as 1 minus 1 upon n square plus 1 whole square. Now we can take LCM. This will be equal to n plus 1 whole square, n plus 1 whole square minus n square, and this will be equal to our minus of 2n minus 1 n plus 1 whole square. So once again, n is very much larger than 1, and we can take minus as common, so this will be a plus. This will be equal to minus 2 upon n for n very much larger than 1. So here also we get, in terms of proportionality, it is 1 upon n. Okay. So energy is not proportional to 1 upon n cube, and okay, so only energy. Now we have to find out the angular momentum. So option C is incorrect. A and B are correct. Incorrect. For angular momentum, L of n is our, you can write this as nh prime, and we are this, and for consecutive we can write our delta of n will be equal to h prime. We need to find out their ratio. Therefore we can say our delta L upon Ln is equal to nh, and this comes as 1 upon n. Okay, one second, I forgot to mention one thing. N plus 1 is equal to over n plus 1 h prime, and here I took a shortcut. Let me put it here. So we have to find out the relative change. Therefore we can write relative will be equal to L plus 1 minus Ln divided by Ln. This gives us L plus 1 h prime minus nh prime divided by nh prime, and this we are going to get only h prime divided by nh prime, giving us 1 upon n. So it is proportional to 1 upon n. So therefore option D is correct. Correct. So this completes all the 15 questions from the year 2015 mains as well as advanced, and 2016 mains as well as advanced. There were 7 questions from 2015 and 8 questions from 2016, consisting of both mains as well as advanced. So this completes all the 15 questions. Thank you.